Okay, we are talking about bonding, I think. So we've been talking about chapter 12, which is bonding. We talked about the three sort of different types of bonding. Ionic bonding, which as we've talked about is between a metal and a non-metal, with obviously our metal transferring our electrons, creating ions, which hold that together. Then we really have covalent bonding, which is really between two non-metals. And because of that, they will share electrons. And as we talked about, they may share those electrons equally, and that is what is referred to as a nonpolar bond. They may share them unequally, which is known as a polar bond. Equal sharing of electrons means that the electrons between those two atoms are going to be equally distributed and essentially create sort of like a neutral bond. There's no real positive side or negative side of that bond. Unlike in a polar bond, we will have one side that is more electronegative than the other, and that will create a separation of charge and a partially negative charge on one side and a partially positive charge on the other. And we could represent that with a bond dipole arrow that points to the more negative side. And obviously, this part back here that makes like a plus sign on that arrow is to the more positive side. We could determine really what type of bond we're dealing with by taking the difference in electronegativity values, as we saw on that table. Anywhere from 0 to 0.4 is considered really a nonpolar bond. Kind of above 0.4, which is, I guess, 0.5, to less than 2 is a polar bond. And not in perfect sort of cutoff, but typically above 2 is ionic. As we talked about a number of times last time, you really don't need the electronegativity values to determine if it's ionic. As long as it's a metal and a non-metal, it will be an ionic bond, so you don't even have to really worry about that. All right, so we're gonna get into drawing Lewis structures for covalent compounds and the steps that you should follow. And you really do want to kind of follow these steps when you're drawing these structures. And you really do not want to do what I sometimes call like piecework, where you try to figure out, how everybody comes together. So we do want to follow these steps, and it should lead you to a pretty good Lewis structure when it's all said and done. The first thing you want to think about is how is everything sort of put together. And in a lot of cases, what you will be drawing most often in this class, even 1A as well, will usually only have sort of one central atom. So there's usually one guy in the middle and everybody's attached to it. It is possible to have multiple central atoms where things are attached to each of them. But in our case, usually we'll have like one and everybody's attached to it. How do you know who should go in the center? So usually the least electronegative element should be in the middle. And usually, again, everything should be sort of attached to that. Remember that electronegativity increases as you go up and right on the periodic table, fluorine being the most electronegative you have. With that being said, that means we should really never, ever put fluorine in the center because it's the most electronegative element. It should always be on the outside. And our friend hydrogen should never be in the center because, again, a really important rule is hydrogen just needs 2 electrons, which means if you put it in the center, it's definitely going to have more than 2 electrons. So hydrogen should always be on the outside. Fluorine should always be on the outside. And again, the sort of least electronegative atom should be in the center. Obviously, logic also plays into play here as well. A lot of times, if you have one element or one atom of one element and multiples of another, usually the one element ends up in the middle and everybody's sort of attached to it. Probably the most important thing that you're going to do when you draw these pictures is number 2 here, which is to count up the total number of valence electrons in the entire molecule. And again, the number of valence electrons equals the group number. And if we do have some type of polyatomic ion or ion that has a charge, you do need to adjust your electron count for your picture. So a reminder that if somebody has a negative charge, that means that it has gained electrons. So you need to add whatever that negative charge is to your total. So if it has a -1 charge, you need to add one more electron to your count. And if somebody has a positive positive charge, we subtract that charge from the total. Again, guys with positive charges have lost electrons, so you need to take that away from your total. This number is really important because this is the number of electrons your picture has to have exactly to the nose. Cannot have any more or any less electrons. It's got to hit that number right on the number there. This is where sometimes people go wrong. They kind of do piecework and they go, okay, well, nitrogen's got 5 valence electrons, oxygen's got 6, and they try to figure out how all those electrons come together. What you want to kind of really think about in terms of these electrons when you calculate them is I want to kind of distribute the electrons sort of as equally as I can to everybody that's in the compound. Not that they belong to necessarily one element versus another. So we just want to kind of distribute all these electrons equally. So how do we do that? Well, the first thing that we want to do is take whatever you have in the center and whatever atoms you have on the outside, and you basically just want to make one single bond. And remember that each line and each bond represents 2 electrons. So that will use up some electrons from your total. You'll still have electrons left over at that point. Those leftover electrons, after you make that one single bond, will go on the outside atoms in pairs of electrons. So you'll pair them up. And again, we're going to try to fill up all the outside atoms until they have 8 electrons around it. So we're just going to kind of, move around pairs. Then if you still have electrons at that point, then we're going to move to the center atom and also put them on in pairs. So again, the idea here is to distribute all these electrons sort of equally outside, working outside in to the center atom. At this point, when you get to the center atom, you should be out of electrons if you're putting dots on it, or maybe before you get there, you might be out of electrons. It's at this point that we want to make sure that everybody has met the octet rule. And if somebody has not met the octet rule, that is where we want to fix it by making a double bond first. And we want to try to exhaust all the double bonds that we can. And if the double bond doesn't fix it, then we want to go to a triple bond. So you definitely do not want a double bond or triple bond right out of the box. You should start with all single bonds and then use like the double bond or triple bond to try to fix something. If somebody hasn't met the octet rule, obviously hydrogen should have 2 only in that case. Any questions on that there? So let's see how this works with a real example. Let's take a look at this. So NF3 is what we want to draw here. So the first thing I'm going to do is calculate the total number of valence electrons in the entire thing. So nitrogen is group 5. There are 3 fluorines, each is group 7. And that gives me 26 valence electrons. So that is the number of electrons that I should have in my picture. So here between nitrogen and fluorine, they are in the same period on the periodic table. And remember, electronegativity increases to the right. So that means that nitrogen is the least electronegative atom. So I'm going to arrange these guys in a logical arrangement. And to answer the question that somebody might have right at this point, yes, you can put the fluorine up on top if you like versus the bottom. It doesn't really matter. So wherever you want to kind of put that third fluorine, top or bottom, it really doesn't matter. At this point, I'm just going to make, again, one single bond to everybody. So I'm just going to draw a line here, big lines. And again, each of these lines represents 2 electrons. So I just used 2, 4, 6 electrons. So if I subtract that off from my total, I got 20 more electrons to put on this picture. Again, these electrons go on the outside in pairs, and then we work our way in if we need to. So we're going to go with 2, 4, 6, and that guy is filled because he already has 2. 8, 10, 12, that guy is now filled. 14, 16, and 18. I just put on there another 18 electrons. That still leaves me 2 electrons basically to go at this point. At this point, those 2 electrons now will go to the center atom, and it will also go on as a pair of electrons. At this point, I've now put on all 26 electrons. What I want to check at this point is, does everybody meet the octet rule? So fluorine here, 2, 4, 6, 8. Really, all the fluorines are identical, 2, 4, 6, 8, 2, 4, 6, 8. And when we look at the nitrogen, 2, 4, 6, and 8 electrons. So everybody has 8 valence electrons. We have put on there a total of 26 electrons, sort of equally spread out. Any questions on that there? So let's take a look at another one here and talk about some other things that you might come across. So let's take a look at carbonate, which I think might be on your handout there. So if we look at carbonate, we're going to do the same thing here. We're going to first count up our number of valence electrons. So carbon is 4, group 4 for the carbon. There are 3 oxygens. Each oxygen is group 6. That's 18 for our oxygens. Now we do have a -2 charge, and that -2 charge means that this thing has gained 2 electrons. As that's the negative means, it gained, and it gained 2 electrons. So I do need to add 2 to my total for the -2 charge. So I'll put the -2 charge there. And if I do all that, that's 18, 20, 24 valence electrons is what my picture should have in this case. Once again, if we look at the periodic table between carbon and oxygen, oxygen is further to the right in the period, and that means that it should be more electronegative. And besides that, I only have 1 carbon, so carbon probably should go in the center here as it's the least electronegative. So I'm going to do carbon in the center. I'm going to put my oxygens around. And once again here, I'm going to do the same thing. I'm going to make a single bond to everybody. So just 1 line to everybody. That again is 2, 4, 6 electrons. So I had 24 I started with. I just added 6. That's a lot of math. That's 18 electrons I think I got left to go. So those electrons here are going to go on the outside atom. So 2, 4, 6, again in pairs of electrons, not single electrons, but pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 at this point. I have now put 18 electrons on the outside atoms, and I am now completely out of electrons at this point. And what I want to do is to make sure that everybody is okay. And if we look at the oxygens here, we got 2, 4, 6, 8. All the oxygens are the same. They all have 2, 4, 6, 8. But carbon here has 2, 4, and 6 only. So carbon is actually short of the octet rule here. So that is a problem. We cannot leave our Lewis structure like this because in this structure, the way it's drawn, carbon has not met the octet rule. We have basically put on all of our electrons there. Try to erase this without erasing my bond. There we go. So at this point, we need to fix it. So can I fix it by just putting some electrons there? I cannot because now I have a total of 26 electrons, so that's not good, and I can only have 24. So this is a situation where we've distributed all of our electrons, and we have not met the octet rule. So this is a situation where we want to first try to fix it by making a double bond. In this particular case, all those oxygens are exactly the same. They're all identical, which means you could really make the double bond at any oxygen that you choose. So when I make a double bond, can I just throw a line in there? The answer is sort of, but we can't just throw a line in because now how many electrons do I have? I now have 26, which is too many, right? In addition, the oxygen on top that I just did now has like 2, 4, 6, 8, 10 electrons, also too many electrons. So when we make a double bond, we cannot just lay up a double bond. By the way, also a triple bond works the same way. You can't just triple bond it out. But what we're actually doing when we're going to make the double bond is we have to take a pair of electrons from that atom we're going to make the double bond with. We're actually going to bring those electrons in to make the double bond. So when we do that, that will then result in a double bond towards the top there. We will still have these guys, which are single bonded. And now when we look at this, we also put a bracket around it because it's an ion, and we put the little charge on the outside to make it look all pretty. But now when we look at this particular structure, we still only have 24 electrons, but everybody now has 8. So we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and for the carbon, 2, 4, 6, and 8. So everybody has met the octet rule. The double bond fixed it. And this is, again, how you want to use double bonds or triple bonds is to fix a problem. Now, like I said before, could you have done the double bond on any of the oxygens? The answer is yes. So if you did not want to double bond the top guy, you could have laid up a double bond over here to the right. And obviously you could have double bonded to the left if you wanted to do that guy. And you could have drew a picture that looks like this also. And all three of these pictures are actually related to each other. These are all what are known as resonance structures. And resonance structures are structures that basically arise in a situation like this where you have a few options as to where you could like double bond and move that double bond around. The reason for that is the electrons that we bring in to make the double bond, they're what are sometimes referred to as being delocalized, which means they're just moving around. So if we look at something like carbonate here, and in terms of those electrons that are making the double bond, at some point they may be over here at this guy, but then they may kind of move over to the top guy. Then those same electrons may move over to the right-hand side oxygen. So those electrons are kind of moving around between the different atoms, which means no one Lewis structure will basically adequately describe what's going on. The real structure is probably somewhere between all three of those pictures, but you can actually draw some, in this case, 3 different Lewis structures to represent the bonding that's happening here. Do you have to draw all the resonance structures all the time? The answer is no, unless you're asked to do so. If you were just asked to draw the Lewis structure for carbonate, any one of the 3 structures there in the middle would be perfectly fine to draw. You don't have to draw them all. But if you are asked to draw the resonance structures, then you need to draw, all the possible places you could kind of move the double bond to and draw a new structure. Any questions on that? Yeah. Yeah. It's just a way when you're drawing Lewis structures for, these are really polyatomic ions. So these are ions basically. So to indicate that they are not a neutral sort of molecule and they are an ion, when you draw the Lewis structure, we put the brackets with the charge on the outside. Um, the alternative to that is if you knew sort of where the -2 charge was, you could actually put the -2 charges on the appropriate oxygens. Those are what are known as formal charges, which we don't really talk about in here, but the actual minuses are actually on those single bonded oxygens, and that those guys together is what makes up the -2 that this guy sort of has. But usually for us, brackets and the overall charge on the outside for anything that has a charge. If it's neutral, you don't need to put brackets around it or anything like that. They're just for charges. Yeah. Other questions? Yeah. Yeah. You could, yeah. So if you were asked to draw just the Lewis structure, you could draw any one of these 3 pictures where you could put in this case, the double bond at any of those oxygens. And it's really because all those oxygens are basically identical to each other. So you could double bond them all the same way. Yeah. It'll be probably fairly obvious. I would say probably in most cases and stuff in this class, you probably are safe to kind of double bond it anywhere you want. But for example, um, we draw something like nitric acid, for example. Oops, 2 dots there. Get rid of that 1 dot there. So if you draw something, say like this nitric acid, in this case, you would have had before you would have double bonded it. for example, it would have looked like that, basically single bonded. In this case, you probably would want to only kind of put your double bond either at this oxygen or this oxygen, the single bonded oxygen, because this guy is actually what makes it an acid, and that's sort of an OH group, is an important sort of group. So you probably, in most cases, wouldn't double bond that oxygen because it's got something else sort of attached to it. But I would say probably in most cases in here, you probably are pretty safe just to kind of move it to all your options would be okay. Yeah. Other questions? All right, so why don't you draw some here? Let's see here. Why don't you draw the Lewis structures for each of these? Let's do SO2. Let's do SH2. Let us do. Why don't you do NO3 minus? Let's do. Let's do N2. And let's do CO2. All right, so draw the Lewis structures for each of these. See what you come up with. Okay, so let's take a look, see how you're doing. We'll start with this one here, SO2. So again, I'm going to start with really figuring out how many valence electrons. So sulfur there is group 6. Oxygen is also group 6, but there are 2 of them. So that is 12, 18 valence electrons. Once again, when we look at the periodic table between oxygen and sulfur, oxygen is further up, which means it's more electronegative. Also, we only have 1 sulfur in this case, so we might as well put that guy in the middle as it is the least electronegative. We're going to put oxygens to the side. Seems like a good idea. We're going to do, again, a single bond only. Again, no double bonding or triple bonding out of the box. That is 4 electrons that we use. We have 14 more to go. Again, on the outside first in pairs. So 2, 4, 6. That guy is filled. 8, 10, 12. That guy is filled. At this point, I have now put on there 16 electrons. I actually still have 2 more to go. And they will now go to the center atom in pair of electrons. And that is how dots get on there, by the way. In this case, we now want to make sure that everybody is good. Is everybody good here? Sulfur is a little short, right? The sulfur in the middle has only 2, 4, 6 electrons, right? Everybody else has 8 electrons happening there. So this is a situation where we could try to fix it by making a double bond. Once again here, both oxygens are identical to each other, so you really could double bond it up whichever side you like. Remember that when we are making the double bond, we're going to take a pair of electrons and bring them in to do so. And that will get us a structure that looks like this with a double bond there on the right, a single bond on the left. This is also one that you could draw a resonance structure for, which is basically you double bond it to the left instead of to the right, which is perfectly fine. And this is what it looks like, by the way. It does not look like 2 double bonds on each side where people will do that. So again, do not double bond out of the box. You do need to have those dots on the central atom. And if you follow those sort of rules, you should end up with those dots on the central atom. Any questions on that? Once again, you could draw either one of these unless you were asked to draw the resonance structure. So. All right, let's take a look at the next one here. So sulfur is 6, hydrogen is 1, so that is 8 valence electrons. We know in this case hydrogen should never be in the middle, so we got to go with sulfur in the middle. Again, hydrogen on the outsides. Going to connect with 1 single bond to each. That's going to be 4 electrons. Leaves us 4 more to go. Am I going to put dots on the hydrogen? No, because I don't want a big X, right? So hydrogen is filled, right? It has 2 electrons. So that means we then go to the center. So again, always outside to inside. And on the center here, they will go on once again as pairs of dots. So we do need to distribute sort of all of our electrons before we think about double bonds or triple bonds. and that is definitely the order you want to do it. At this point, everybody's good. Hydrogen has 2, and each of the hydrogens have 2, and the sulfur there has 8, 2, 4, 6, and 8 electrons around it. Any questions on that one there? So rolling through here, we'll go to the next one. We got nitrogen, which is group 5. We got 3 oxygens, which is group 6. And we do have a -1 charge, which means it has gained an electron. So we do need to add it, bless you, 18, 19, 24 valence electron. Again, here, looking at the periodic table, nitrogen, oxygen, the same period. Oxygen further to the right, more electronegative. That means nitrogen here should go into our center spot, which is being the least electronegative. We're going to single bond up here. That's going to give us 2, 4, 6 electrons. Again, leaving us 18 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, once again, I have placed all 24 electrons. And you hopefully should see that our guy right here in the center is a little short. He only has 6 electrons. So again here, as you can see as well, all the outside atoms are the same. So you can double bond anywhere you like. We're going to try to fix it by double bonding by bringing that pair of electrons in. That would get us a double bonded oxygen up on top and our single bonded oxygens on the outside. And again here, because this does have a charge, we would put little brackets around it with the negative. This again is another one we could obviously draw just like carbonate, basically a couple other resonance structures. You could have again double bonded there to the left. Or you could have double bonded there to the right. And it would look something like this. And in this case, just like carbonate, we have 3 resonance structures basically that are equivalent to each other. Any questions on that one there? All right, looking at CO2 here, which is our next one. Carbon is 4 and oxygen is 6, and there's 2 of them, so that's like 12, 16 valence electrons. Once again, carbon, oxygen in the same period on the periodic table. Oxygen further to the right, meaning it's more electronegative. So that means carbon should go in the middle, which is the least electronegative element there is. So we're going to put our carbon in the middle. Going to put our oxygens on the side. Going to do a single bond to each, which is 4 electrons. And that means that we have 12 electrons still to go off of our 16. So we'll go on the outside. So 2, 4, 6, 8, 10, and 12. At this point, we have now put on all 16 electrons. Is everybody good here? Carbon is definitely well short, right? Carbon in the middle has only 4 electrons. So we want to fix it by making a double bond. Again, you could do it at either oxygen here. So I'm going to bring a pair of electrons in to do so, and that's going to double bond me up the guy on the right. Did that fix the problem? It didn't. It got better. Carbon's now up to 6. So this is a situation like we were talking about earlier. You do want to exhaust all your double bond possibilities, right? So I could actually double bond the other side as well before you move on to a triple bond. So kind of before you jump to a triple bond, if there's an option to do another double bond, that's what you probably should do first before the triple bond. So to do the double bond on the other side, we're going to do the same thing. We're going to bring it in, and that's going to give us a double bond over here and a double bond over here. And at this point, we now have still only 16 electrons, and everybody now has 8. So our oxygen 2, 4, 6, 8, our oxygen on their side, same thing, 2, 4, 6, 8. And our carbon, 2, 4, 6, 8 by the double bonds on both sides. Any questions on that one there? So again, you want to kind of exhaust your double bonds before you move on to your triple bonds. And lastly here, we got N2, which is 2 times 5 is 10 valence electrons. In this particular case, there's actually no center atom, so you're just going to line them up in a straight line, basically side by side. And you could still follow the same steps, which means I'm going to connect them. So that's 2 electrons. I have 8 to go. Doesn't really matter which nitrogen you put them on. So we'll start over here on the right. So 2, 4, 6, and 8 in this case. Are the nitrogens good? No, the nitrogen on the left is short. It has only 4 electrons. So we follow our steps. We're going to make a double bond by bringing these in. And when we do that, we will get a double bonded nitrogen in between. Did that fix it? It did not. Our nitrogen on the left is still short. It has 6. There's no other possibility for double bonds in this case. So now we can move to a triple bond. And it works the same way. We got to take another pair of electrons and bring them in to make the triple bond. And that will get us our triple bond in the middle along with these guys. And that is how nitrogen gets to a triple bond. And again, at this point, we only have 10 electrons and everybody has 8 through sharing that triple bond. Any questions on drawing Lewis structures for covalent compounds here? Yeah. All right, we will lay it up there for now.